Okay, so we have defined joint moment generating function of random variables last Tuesday. Now, I will list two propositions on properties of joint moment generating function. Okay, so assume that the joint moment generating function of n random variables x1, x2, 2xn is defined on a neighborhood on a neighborhood such that of the origin zero vector in Rn. Okay, then x1, x2 up to xn have all joint moments m sub k1, k2 up to kn, which this joint moment is that x1 raised to the k1's power, x2 raised to the k2's power, up to xn raised to the kn's power. All right, so that this random variable have all joint moments, and the joint moment generating function has partial derivative as part of any order at the origin. Such that the joint moment m sub k1, sub k2 up to sub kn can be computed by evaluated the partial derivative Okay. Okay. The part derivative at the origin. Right, so, and the proof actually is an extension of proposition 7.7.h. Alright, this proposition is for non-generic function of a single random variable. All right, another useful proposition is in proposition 7.7.j. Again, assume that the joint moment generating function of random variables is defined on a neighborhood of the origin in n-dimensional Euclidean space. Then we have 4 properties. The non-generic function of the ith random variable it actually can be defined from the joint moment generic function. The ith coordinate. Okay. The second net, there is 1-to-1 correspondence between the set of joint CDF each of which has a joint moment generating function It's a joint moment function defined on a neighborhood of the origin in Rn. And the set of their joint moment generating functions. Okay, so again we have a one-to-one correspondence. And the third one, x1, x2 up to xn are independent random variables, if and only if the joint moment generating functions of this n random variable is the product of moment generating functions of individual random variables. Okay. Of course, that the parameters here used will be different. They are in T1, T2, and Tn here. Okay. So that the third item in position 7.7j it's give us a way to check whether n random variables are independent random variables. Okay, just by showing that their joint moment generating function is the product of the moment generating function of each random variables. Okay, but of course that the parameters used in the moment generating function of individual random variables will be different. Okay, and the fourth item here is that x1, x2 up to xm and x sub m plus 1, x sub m plus 2 up to xn. Okay, so we divide the n random variables into two collections, and these two collections are two independent collection of random variables, if and only if the joint moment generating function of these n random variables is the product of the moment generating function of these two collections times m okay. So the proof is here. For the first item, For the first item, we know that the moment generating function of the ith variable, as we know by definition, is here. So that you can see this is 0 times x1 plus plus 0 times x I minus 1 plus t times xi plus 0 times xi plus 1 plus plus 0 times x of n. Okay, so you can see here. And so that this is okay. All right, and the one-to-one corresponding, so this follows from the inverse bilateral multiple Laplace transform. Okay. And 3 and 4 so this follows from proposition 7.2.c and item 2, okay, in above, and 4 also, okay, right. The last section in chapter 7 is about additional property of normal random variables. Okay, but in this class lecture, I would like to cover the material in a more general setting. Okay. All right. So first, in this section, all random variables considered have second moments, has finite second moment. Okay. Now the first subsection is about covariance matrices. All right, so first of all, we define the covariance matrix. Lambda of n random variables x1, x2 up to xn as here. So we just put all the covariance between these n random variables in a matrix. So the first entry will be the covariance of x1 with itself. Okay, so that this is just the variance of x1, and the second is covariance x1 and x2 up to covariance of x1 and xn. The second row will be covariance of x2 with x1, covariance of x2 with itself, and covariance of x2 with xn. The last row will be the covariance with xn and x1, the covariance of xn with x2, and the last will be the covariance of xn with itself. Okay, so you can see that this matrix contains all the covariances between any two of these two random variables, or of these n random variables. All right, so that is, okay. And when we look at this matrix, so you can see things the covariance between xi and xj is equal to the covariance between xj and xi. Right, so this is from proposition 7.4.2-1. All right, so the covariance matrix the covariance lambda of n random variables x1, x2 up to xn is an n times n real symmetric matrix, i.e. the transpose of this matrix is equal to lambda. Okay. Right, so this is the first observation to see that covariance matrix always a real, because we are considering real value, random variables here. So the covariance are real numbers, and so the covariance matrix here is an n times n real symmetric matrix. Okay, and now recall from linear algebra. Okay. And n times n real matrix U is called orthogonal if U multiplied with U transpose is equal to the U transpose multiplied with U is the identity matrix. N times n identity matrix. Okay, so a an n times n real matrix is called orthogonal if it has these properties here. So it is clear. So now, so you can see that if U is expressed as okay, here Ui, the ith column of the U. And so the U transpose, you come to U1 transpose, U2 transpose, up to UN transpose here, right? So, okay, so U1 are column vectors, and the transpose of a column vector becomes the row vectors here. Okay, so U times UT, so you can see U, T, and U would becomes to be U1T, U and T, U1, U2, UN here. Okay, so you can see this U1T, U1, U1T, U2, up to U1T, UN, and this is U2T, U1, U2T, U2, U2T, UN, okay, up to UN T transpose U1, UN transpose U2, UN transpose UN, okay, and this is equal to 1, 0, this is the n times n identity matrix. Okay. All right. So when we look at the product, because this product is equal to this identity. Okay. And so from here we know that so this implies that U, I, T, U, J. Okay, so this is U, I, inner product with U, J is equal to the delta Ij. Okay, so this is 1 if I equal to J, and 0 if I not equal to J. Okay. Right. So the inner product between any two columns of an orthogonal real matrix, right, is either 0 or 1. Okay. So if we use two different columns, then their inner product will be 0. So they are orthogonal. Right? So the columns are orthogonal to each other. And when I equal to J, then the inner product with itself is equal to 1, so that every column matrix is normalized, which means that it has length equal to 1. Okay? So this is the reason why this matrix U is called orthogonal, because that the n columns of this orthogonal matrix are orthogonal to each other. Okay, so they are orthogonal to each other. So it is clear that the columns of an n times n real orthogonal matrix U, okay, they form an orthonormal basis for the n-dimensional Euclidean space, and so do the rows of U. Okay. So if you use this equal to identity, you can show that the rows of U are also normal to each other. Okay. All right. So they form also normal basis because Rn has n dimension, and we have n columns. They are assigned to each other, so they must be linearly independent, right? And this is the largest possible independent set. Okay. Okay. So we know that we have these properties here. Yeah. Now, real symmetry matrix, all right, has a very important property we call the real spectra theorem in linear algebra. The real spectra theorem says that okay. All right, so an n times n real matrix A is symmetric if and only if and only if there exists an n times n real orthogonal matrix U, and n times n real diagonal matrix D, such that A can be written as U multiplied with D multiplied with the transpose of U. And where the diagonal entries of the diagonal matrix D are eigenvalues of this matrix A. Okay. Alright, so real symmetry matrix can be characterized by a real spectra theorem here. Okay. So a real matrix A is symmetric. Okay, symmetric. If and only if that this matrix can be expressed as the product of an orthogonal matrix D and a diagonal matrix D, U, orthogonal matrix U, diagonal matrix D, and the transpose of this orthogonal matrix. Okay, and the diagonal entries of this diagonal matrix are eigenvalues of A. So So it contains all eigenvalues of the A. Of course, the eigenvalue may be repeated, so we may have a multiplicity. Okay. Anyway, all right. So this is a very important theorem in linear algebra. Okay, and by construction of the covariance matrix, so we know that any covariance matrix has this property. Okay, so that it has spectral decomposition. Okay, so this is called right. So that if we look at okay, and here we have U1 transpose, U2 transpose up to, okay, so if we write this way, and so U1, U2 up to UN are n columns of this orthogonal matrix. And when you multiply them, you will find this is equal to UI transpose. Okay. Okay. So the matrix A can be expressed by the eigenvalues of A, and of course that also from here we know that A U equal to UD U transpose U, right? So this is UD. Okay, because that U TU equal to identity. All right, so AU equal to UD. Now, here, so A, U1, U2, UN equal to U1, U2, UN, and you have lambda 1. Okay, so that this is equal to lambda 1, U1, lambda 2, U2, lambda n, UN. Okay, so the product of these two matrices has n columns, which is the first column is the first eigenvalue lambda 1 times the first column, etc. So that we have A UI is equal to lambda I UI for all I. Okay. All right, so this means that UI is an eigenvector of A corresponding to eigenvalue lambda I. Okay, so and this is called a spectral decomposition of A. Okay, this is right. So you can see this is the spectral decomposition of A. Why we call it spectral decomposition is because that you can express A matrix as the summation of the eigenvalue and this product. This product actually is a matrix. Okay, it's a matrix. So the UI, the column matrix times the row matrix become to an n by n matrix with rank 1. Okay, so the rank of this matrix is 1 here. Okay. Okay, so that any covariance matrix has a spectral decomposition. Okay. All right, now to further categorize the covariance matrix, lambda of n random variables x1, x2 up to xn, we express the covariance matrix lambda in the vector form. Okay. Now we let, was implicit, we let mu I to be the expectation of xi. Okay. So be the mean of x sub I. For I from 1 to n. Okay, so now we know lambda so the covariance is actually the expectation of this product. Okay, so the covariance of x1 and x1 is this one, and the covariance between x1 and x2 okay, is this expectation. Okay, so up to right, and the expectation of x2 minus mu2 right? Okay, so we now from the definition we can see that okay. All right, and expectation. So we can express this as the expectation of a matrix of random variables. Okay. So here we have x1, mu1, x1, mu1 here. So expectation, because they're all, so we express this as the expectation of a matrix of random variables. Okay, mu1 and xn minus mu(n), x2 minus mu2, xn minus mu(n) times xn minus mu(n)2. Okay. And we see that this matrix is actually the product of a column vector of random variables. Okay, here. Right. So this vector and the expectation. All right, and then that this will be called expectation of x minus mu times x minus mu transpose. Okay, so we define this. This is actually a difference of two column vectors. Okay, and this is the transpose of these column vectors. Okay. Now, so where x is the random vector by collecting this n random variable together as a column vector, and the mean vector collect all means of the n random variables. Okay, so we have this one. Okay, so now we are able to express the covariance matrix as the expectation of the product of these two, of the product of this column, the random vector and the transpose of the random vector here. Okay, right now, for any vector A, A1, A2, up to AN, all right, in Rn, usually we express vector in Rn as a column vector, okay? So, and consider the quadratic form. Okay, so the quadratic form, A transpose lambda A here. Okay, and so this is actually A1, A2, and the lambda. So we have covariance all right, and A1, A2. All right, so when we multiple out, so this is the quadratic form of the lambda matrix. So this is I from 1 to n, j from 1 to n, ai, and covariance of xi, xj, and aj. Okay. Right, so quadratic form, right, is important in the study of linear algebra. So we have this, okay, the quadratic form of the covariance matrix. Lambda. Then we have that. So we A transpose, and the transpose A2, and we express covariance matrix lambda as expectation of the random vector and the transpose of this random vector A here. And the bilinearity of expectation, so A transpose okay, it's here. All right, and as you can see, this is the row vector, this is column vector. Okay, so this multiplication is a random variable, and so this is we call y. Okay, and so this is the same equal to y, because that this is inner product actually. All right, so this inner product of A, column vector A, and the random vector capital X minus capital U, mu here. Okay, so this is equal to the second moment of a random variable y, and of course we know this is always non-negative, where y is defined to be A transpose of mu here. All right, and also this is also equal to transpose of A here. Okay, and this is actually A1 x1 minus mu1 plus A2 x2 minus mu2 an. Okay, so you can see y is a linear combination of x1, x2 up to xn plus a constant. Okay. So we can see that any quadratic form of the covariance matrix has value which is non-negative. The value will be greater than or equal to 0. So this is a very special property of a covariance matrix. Okay, so that is important here. you see, from here we know the covariance matrix is a real symmetric matrix. So by the real spectral theorem, that lambda has a spectral decomposition. Okay. Now, also we see any quadratic form of the covariance matrix will be non-negative. So that is very spatial, and we will see how spatial it is. All right, and so we know this is Y here. Now, and equality holds if and only if. So this second moment is equal to 0 if and only if the Y, so Y is A transpose, okay, must be equal to the 0, must equal to 0, oh sorry, with probability 1. Okay, so the second moment of a random variable Y is 0 if and only if this random variable Y is equal to 0 with probability 1. Okay, so which means that the n-random variables x1, x2, up to xn has satisfied linear relation with probability 1. Okay, so they are linearly related. Okay, so this shows that the quadratic form, A T lambda A of the covariance matrix lambda is non-negative for all vector A in Rn, and we know that A transpose lambda, the quadratic form, is 0 if and only if A transpose it's 0 with probability 1. Okay, so we have these properties. So any matrix, any real symmetric matrix which okay, all right, so we again recall a concept in linear algebra. An n-transen real symmetric matrix A is called non-negative definite. Non-negative definite. Or non-positive definite. If the quadratic form A of A is non-negative, or non-positive, for all vector A in I. Okay. So from this definition, since the covariance matrix is a real symmetric matrix, and the quadratic form of lambda is non-negative here. Okay, for all A in Rn, so that any covariance matrix is non-negative definite matrix. Okay, so from this definition. All right, and it is further called positive definite or negative definite if the quadratic form A transpose A of A is positive or negative for all A in Rn except the zero vector, because when A is the zero vector, the quadratic form is zero always. Okay, so that in the real case, to say a matrix is negative definite, non-positive definite, positive definite, or negative definite, this matrix we consider must be symmetric. Okay, so symmetric is very important. Okay, it's very important. In a complex case, the definition is much more simpler. Okay, it's more simpler, but for the real case, right, we need a symmetric. Okay. All right, so now there is a characterization. Characterization of real non-negative definite or positive definite or non-positive definite or negative definite matrices. Okay, all right. So okay, and n times n real symmetric matrix A X non-negative definite or positive definite or non-positive definite or negative definite if and only if all right, because we are considering real symmetric matrix. Any real symmetric matrix has a spectral decomposition by the real spectral theorem, okay? So that it has n eigenvalues, of course, with multiplicity, okay? All right, so we can characterize non-negative definite or positive definite, non-positive definite, negative definite matrix in terms of the eigenvalues. So if only if the eigenvalues of A are all non-negative or all positive or all non-positive or all negative. All right, so we can actually characterize a real symmetric matrix to be non-negative definite or positive definite or non-positive definite or negative definite in terms of its eigenvalues. Okay, its eigenvalues. Okay, so that is a very simple characterizations of non-negative definites or the other three kind of definite matrices. Okay, so with these concepts from and the results from linear algebra, so we can say that since the covariance matrix lambda of n random variables x1, x2 up to xn is non-negative definite. Okay, the eigenvalues of lambda are all non-negative. Okay, so they are all non-negative. And lambda is positive definite, which means that all eigenvalues are positive. Okay, so that there is no zero eigenvalues, and because there is no zero eigenvalues, even only if lambda is non-singular. Okay, it's non-singular. So if the covariance matrix is invertible, then it cannot have zero eigenvalue, and so all the eigenvalues of lambda must be positive, and so lambda should be positive definite. Okay. Well, so if lambda is non-singular, that is very good. Now we consider a case that lambda is singular. All right, and so let R be the multiplicity of eigenvalue 0 of lambda. Okay, so because lambda is singular, which means that 0 is an eigenvalue of lambda, and we let R to be the multiplicity of the eigenvalue 0. And we know that the multiplicity of eigenvalue 0 is the dimension of the null space of lambda. Okay, of the lambda. Now it is clear that R is between 1 and n. Okay, and the rank of lambda is k equal to n minus r by the rank nullity theorem in linear algebra, which is a very important theorem in linear algebra. Okay. Okay, now we let V1, V2 up to VR be orthonormal eigenvectors of lambda corresponding to the eigenvalue 0. Okay. Right. So this is actually the null space. So V1, V2 up to VR is an orthonormal basis for the null space of lambda. Okay. And because the null space has R dimensions, so we have R orthonormal eigenvectors. Okay. Corresponding to eigenvalue 0 here. So then we have lambda Vi is equal to 0 for all I from 1 to R. And then your quadratic form forms Vi transpose lambda Vi, which is Vi transpose and 0, and which is 0 for all I from 1 to R. Okay, so now the quadratic form for each Vi is 0, but we say that any quadratic form is 0 if and only if the A transpose, the inner product of A and this column vector is 0 with probability 1. Okay, so this says that Vi transpose X minus mu, it's the 0 with probability 1 for all I from 1 to R. Okay? So the quadratic form is 0 if and only if that with Vi here, Vi and the inner product of Vi and this difference is 0 with probability 1. Alright, and so we know this is actually a linear relationship, okay, among the n-random variables. Okay, so we have linear relationship here. Okay, and then we can collect them together. So V1 transpose, V2 transpose up to VR transpose. And mu equal to 0 with probability 1. Okay, so we collect I equations. It comes to a matrix equation here. Okay, so and we call, so that this is called W and X minus mu equal to the 0 vector, sorry. This is the 0 vector here. And the W matrix is an R times N matrix. Okay? And this is column matrix N times 1. Okay, so the 0 vector is R times 1 here with probability 1, where the W matrix is defined to be okay, so we have that. Okay, and so this matrix has dimension R times N. Okay, we have that. So now, you express right? So that the matrix W has n columns, okay? And the dimension of these columns is R, okay? So they are is R dimensional, okay? R dimensional. So without of generality, without loss of generality, we assume that the last are columns. Okay, the last are columns. All right, so that's n minus r plus 1, n minus r plus 2, up to, all right, so the last are columns of W form a linearly independent set. Form a linearly independent set. Of vectors in R. Okay. First of all, we know that because V1, V2, and VR, they are orthogonal to each other, so they are linearly independent. Okay, and so we have R linearly independent rows. Okay, so the rank of W is R. Okay. Okay, so I have to say the rank of W x R. Okay, since there are rows are linearly independent. Okay, so the rank of W is R. Right, and the rank is also equal to the column ranks, so that the n columns span the n columns here has column space which is R dimensional. Okay, so we know that R out of the n columns must be linearly independent. So we can find a set of R columns which is a linearly independent set. All right, and so we assume the last R columns form a linearly independent set of vectors. Otherwise, if this is not the case, well, otherwise we just permute, because R out of these n columns must form a linearly independent set, right? And there may not be the last R columns, but well, we just permute the n columns of W, and of course do the same permutation on the random variables x1, x2 up to xn in the random vector x. Okay? So if we do the permutation of the columns, we actually do the same permutation on the coordinate on the components of these column vectors. Okay? As well as their means. mu1, mu2 up to mu(n) in the mean vector mu here. Okay, so we because if we permute the columns, we should permute the components of these column vectors. Okay, so they will match to each other. So so after permutation, then the last R columns will be linear independent. And so we partition W as here minus W1, W2. So W is R times N, here is R times R, and here's R times N minus R. Okay? Right, so the last R columns form a submatrix here called W2. Okay. And since W2 since the R times R matrix W2 has are linearly independent columns. It is invertible. All right? It is non-singular, so that it is invertible. Okay? And now we so also we decompose X into two parts. Okay, so here we have R component, and here we have N minus R component here, and mu vector to be mu1, mu2. Here we have R component, minus R components here. Okay, and N minus R is the rank, K. So this is K here. So now we have here so W times X minus mu is 0 with probability 1. Okay? So which means that, and we have Okay. So this is 0. Okay, and so we have, so now W1 times this one, W2 times this one, and so we have W2, X2 minus mu2 equal to W1, X1 minus mu1. Okay, with probability 1. Okay, and because W sub 2 is immutable, so we have with probability 1. Alright, and so X2 can be expressed as a matrix times X1 plus mu2 minus with probability 1. Okay, so which shows that X2, alright, so the random vector X2 is an affine transform of X1 with probability 1. So basically, you can see that the last R random variables can be obtained by affine transformation of the first K, all right, random variables. So they are linear related. Okay, they are linear related. Right, and so since the original one okay, so we have okay, so this is K times K, and with probability 1. Okay, right, so we know here. So now the covariance matrix so the covariance matrix lambda becomes to, so lambda okay, so we just plug into it. So this is the linearity of expectation. So this is X1. Okay, and here transpose. All right, and so you see that okay, and so this is the covariance matrix of X sub 1. Okay, where is the covariance matrix? Of X1, which is Alright, so this is the covariance matrix of the first k random variable. It's x1, x2, up to xk. Yes?
From the third row, how you change omega 1 by omega? From the third row.
This one?
Yeah.
You mean?
The second row is omega 1 times x1 minus mu1. Yeah.
Yeah, but if you move to the right hand side, right? You mean the W or mu? This one? Okay, this minus times plus is equal to 0, right? Yeah, and you will move this term to here.
Yes, I mean the citation W1. Notation W1.
W1?
Yeah. But you write W.
Oh. Where? Oh, here, yeah, thank you. Oh, yes. Thank you so much. Okay, good. All right. Yeah. Thank you for the correction. Okay, good. So, now, since lambda has rank k, right? And so lambda has rank k, right? And now this is the n times k matrix, and this is k times k, and here is k times n. Okay. So the rank of this product is less than or equal to k. Okay, depends on that. But we know this product has rank k. So the lambda x1 must have rank k too. Why? Because if the rank of this central matrix, the rank of this one is less than k, then the product has rank less than k. Okay, that the rank can be smaller than the rank of this central matrix. All can be equal, right? So that the rank of this one must be equal to k. Right? Since the rank of lambda, since the product lambda is the product of these three matrices. All right, so this is, so that must have 2, and then, okay, it's non-singular. Right, so this matrix is non-singular, and so we summarize. So we summarize the above discussion in the following proposition. Okay. So we call proposition 7.8.a. The covariance matrix lambda of n random variables x1, x2 up to xn is n times n real non-negative definite matrix. Okay, to be real non-negative, that means, of course, it must be symmetric by definition. Now, it's non-singular if and only if it is positive definite. Okay, and if it is singular and of rank k, and the k is in between 0 and n minus 1, right? Then R, which is defined with n minus k, are out of the n random variables xi, r, and affine transform of the rest k random variables with probability 1, right? And this k random variables has covariance matrix is singular, non-singular. Okay. So this proposition is a very strong proposition. Okay. It says that the covariance matrix tells us a lot of information, especially when the covariance matrix is singular. Okay. Means that it is not a full rank. Okay. So that so if the rank is k is less than n, then n minus k variables among the n variables are affine related to the rest k random variables, which means that r random variables can be obtained by linear combination plus by linear combination of the rest k random variables plus a constant. Okay, so they are linearly related with probability 1. This is a very strong relationship. Okay, this is a very strong relationship, and all we know is that the covariance matrix is singular. Okay? Okay. And it has a profound implication in signal processing, okay? And as well as in the communication systems theory. Okay. All right, so in the next subsection, we'll consider jointly normal random variables. All right, first of all, we relate Z1, Z2 up to Zn be an independent standard normal random variables. They are standard normal random variable, means that they all has zero means and the variance equal to 1. Okay. Right, and that's x1, x2 up to xm, bm random variables such that x1 is obtained by linear combination of this n-independent standard non-random variable plus a constant mu1, x2, plus mu2, etc. up to xm. Okay. Right. So if this n random variables is obtained in this way, then x1, x2 up to xm are said to be jointly normal or to have multivariate normal distribution. Okay. Now, this is a system of linear equations. So we will write in vector form. So vector form okay, and here is Z1, Z2 up to Zn. Okay, plus mu1. So it's A, Z plus mu. Okay. Okay. So this n linear equation can be written as a matrix equations here. Okay. Okay. So this A matrix here and Z matrix here and here. Okay. Okay, so now the covariance matrix lambda of these n random variables x1, x2 up to xm is, so we know that, but before that I have to see that the mean vector of x of the random vector x here so it's A plus mu here, and by linearity of expectation we know this is EZ plus mu here. Okay, and this is A times the zero vector plus mu. Okay. Since the mean vector of the running field is the zero vector. Okay, it's a zero vector there. So we have, so that the mu here is actually the mean vector. Okay, and so the covariance matrix lambda of the n random variables x1, x2 up to xm, x here, the transpose. Okay. All right. But as we know from here, which means that x mu is equal to AZ. Okay, so that the expectation of AZ transpose. So this is A, expectation of Z transpose, and A transpose here. Okay. And this is A, identity n times n, and A transpose. So it's A times A transpose. Okay. Since the covariance matrix is the identity matrix. Okay, since the covariance of Z I Ij is equal to the delta Ij for all. Okay, so we have that because Z sub i's are independent standard normal random variables. So we have, so the covariance matrix of Z is the identity matrix. And the covariance matrix of the m random variables, x1, x2 up to xn, this lambda is actually is the A times A transpose. Okay? Okay. So A is just the coefficient matrix of this system linear equations here. Now, the join PDF of Z sub J's, right? Because that they are independent and absolute continuous random variables, so they have joint PDF. All right, and so it is the product of is the product of the PDF of each Z sub J. Okay. So that this becomes to be n's power and the exponential minus okay, and so that this is 1 over square root n's power and the exponential function of minus 1/2 and the z t z. Okay. Right, so this is the joint PDF here. Now I'll state the position 7.8.b. If m is equal to n and the coefficient matrix A is a non-singular n times n matrix, then the n jointly normal random variables x1, x2 up to xn are jointly absolute continuous with joint PDF okay, which is length power and the determinant of lambda and the exponential function of minus 1/2 x minus the mu vector transpose and the inverse of lambda and okay, where lambda is A times A transpose is the covariance matrix of X sub i's. Okay. Okay. So if we have the same number of equations as the number of z1 variables, which means that if m equal to n, and the coefficient matrix is non-singular, okay, in this case, then the n jointly normal random variable x1 up to xn are jointly absolute continuous with a joint PDF in this form. And the proof is that we know that consider a function x of z, which is the linear function. Okay, so this is a coordinate transformation on Rn since A is invertible. Okay, because A is invertible, so this mapping G, so G is a vector field. Okay, it's a vector function defined on n-dimensional vectors. So it's a coordinate transformation. All right, as we consider in chapter 6 there. Okay, and so by proposition 6.7.b, okay, because the z, right, the n random variables x1, x2 up to xn are jointly absolute continuous with a joint PDF, okay, f of is equal to f of z divided by the s value of the Jacobian determinants, okay, here, right. And so now the Jacobian of the G matrix, so know that the Jacobian is actually a constant matrix. Okay? So that because this is an affine transformation. So the Jacobian, and also, and this is invertible, of course. Okay. So for all z in Rn, okay. So the Jacobian matrix is, determinants. I'm sorry here. The Jacobian matrix, okay? So all C in R. Okay. Okay, so and then the z, right? The joint PDF of z sub I is in here. So we have 1 over square root of 2 pi n. But this is the absolute value of the Jacobian determinants. So when you put into the square root, then you have determinants of A, but you take the square here. Okay? So you take the square and you take the square root, you get the absolute value of the Jacobian determinants. All right? And also exponential function 1 over this is z, t, and z here. Okay? Now, but z is actually, so also here, we know that az equal to x minus mu. All right? So this implies z is equal to the A inverse of x minus mu. Okay. So we do that. Two pi and here, and determinants of A and times determinants of A transpose. Okay, because the determinant of A transpose is equal to the determinant of A here. Okay, so we put the substitution here. Okay, and so this is one of, and by the product formula of determinants, we get determinants of A transpose here. Okay, and this is exponential function of, okay, and X mu transpose A inverse transpose and A inverse. Okay, mu here. Right, and since A inverse transpose is equal to A transpose inverse, okay, and A inverse transpose A inverse equal to AT inverse, A inverse. So this is the A transpose inverse. So this is lambda inverse here. Okay, right. So this is actually equal to lambda inverse. Okay, so we have the joint PDF is equal to, okay, and this product is equal to lambda, okay. So 2 pi n determinants of lambda and the exponential function of minus half X minus mu lambda inverse transpose. Okay, so this is the end of the proof here. Right. Okay, so we know the case that if the coefficient matrix AX non-singular is a square matrix and is non-singular, then the joint normal random variable x1, x2 up to xn must be jointly absolutely continuous, and it has a joint PDF has this form, which is determined by the mean vector as well as the covariance matrix of this joint normal random variables xi's. Okay, right, and to compute, so we can compute the joint moment generating function of the joint normal random variables x1, x2 up to xm. Okay, so that m x1, x2 up to xm, t1, t2 up to tm. So we know that this is the expectation. Alright, so our task is to find this joint normal Jacobian function of the m jointly normal random variables. We observe that, right, for fixed parameters t1, t2 up to tn, the y, okay, right? Y is the linear combination of xi, right? And because we fix t1, t2 up tn, so we use t1, t2, tn as coefficient to find a linear combination, right? And so, but each xi is an affine, is a linear combination of this subject plus a constant, okay? So that's by regrouping, we have Ti and Aij, Zj plus summation I from 1 to m, and Ti and the mu I here. Okay, so y, when we look at, so y is a sum. It's a sum of independent normal random variables, Zj's, okay, and a constant. All right, and a constant. So that y is a normal random variable. Okay? Right. So independent, so that this is, so this one is okay. So a coefficient times Zj give us, so that they are independent normal random variables. Oh, they are in the constant. I have to say right? So this random variable are normal, independent normal random variables and a constant. Okay, as the independent sum of independent normal random variable by proposition 6.3. I think 0.1 for normal, or 2. Yeah. Anyway, as we discussed, that this sum must be a normal random variable. All right, a normal random variable, and you plus a constant. So again, it's a normal random variable. Okay, so that y is a normal random variable, right? With mean All right, so the mean is so by linearity, all right, so this is the mean, and so we use the transpose of T vector where T vector would be T1, T2 up to Tn transpose. And covariance and variance and the variance. Okay. So we find the variance. So the variance of okay. Ti covariance of Tk, and this is T transpose lambda T. So it's this quadratic form. Okay. So the variance of y is this quadratic form here. Okay. So now we know the monitoring function of a normal random variable, right? So this is it's just the mean of y times t plus 1/2 of the variance of y times t squared. Okay. So now we have x1, x2, xn, t1, t2 up to tn. So this is expectation of E of y. Okay, E of y, because y is the, by our definition, y is this linear combination. Okay. So this is n of y with t equal to 1. Very interesting, right? So that this is the joint monitoring function, right, of x1 up to xn. X actually equal to that the monitoring function of y, but when t equal to 1. Very interesting. So that this is exponential function of, and the ey, you see, is here, mu here, plus 1/2, and the variance of y, because t is equal to 1, right? It's 1 here. So that we will say. So this is Ey plus 1/2 of the variance of y. Okay, because t equal to 1. Okay, and so this is the exponential function of, so we do the substitution, t transpose mu plus 1/2 and the quadratic form. Okay, it turns out very simple here. Okay, so so we know that if this m random variable are joint normal. If they are jointly normal, then their joint moment generating function has the exponential form. Okay, you can see here, and this joint moment generating function is determined by the mean vector and the covariance matrix of this m jointly normal random variables. Okay. And so now I'll state a proposition here. Which says that, if n random variables, x1, x2 up to xm, have a joint moment generating function, which is the exponential function of grass Okay, so have a joint moment generating function which is equal to this one, where mu and lambda are the mean vector and the covariance matrix of xi's, then they are jointly normal. So they are jointly normal, and the x, the random vector, is equal to a times z plus mu with probability 1. Okay? With probability 1 for n times n real matrix A of rank n of rank n, which is equal to the rank of the covariance matrix lambda, and a random vector z, okay, where z1 whose components z1, z2 up to zn are independent standard normal random variables. Okay, so this gives us the converse. Okay, so if we know that n random variables have joint moment generating function, take this form here. Mu is the mean vector and the lambda is the covariance matrix of this m random variables. Then these m random variables are jointly normal, which means that we can find a matrix A, we can establish such a linear equation with such a system linear equation with probability 1. So that the random vector x matrix A times random vector z plus the mean constant, the mean vector mu here. And A is a matrix has the same rank as the rank of the covariance matrix lambda. Okay? And the component of Z, which is Z1 up to Zn, are independent standard normal random variables. Okay? So this proposition gives us the converse of our discussion. Okay. And an application okay, so the proof right? So I will distribute lecture notes for the proof. And there are two propositions, okay, and will be taken as exercise. So let x1, x2 up to xn be jointly normal random variables with a covariance matrix lambda equal to here. Right? So we have n jointly normal random variable with a covariance matrix. Then x1, x2 up to xn are independent random variables if and only if lambda, the covariance matrix, is a diagonal matrix. Okay. So it's very simple to identify independent joint normal random variables. Well, we just check that the covariance matrix is a diagonal matrix. Right, and so the proof as an exercise. Okay. And the last proposition given in today will be, so let x1, x2 up to xm, y1, y2 up to yn be jointly normal random variables with a covariance matrix lambda. Right? Then the X collections and the Y collection are two independent collections of random variables if and only if lambda is block diagonal. So lambda can be written as lambda x 0, 0, lambda y, where lambda x covariance of xi prime is the covariance matrix of xi's and lambda y is the covariance matrix of yj's. Okay? And so the proof is also as an exercise. Okay. Right. So for joint normal random variables, the important thing, all the information needed is just the mean vector and the covariance matrix. And so that their properties can be seen from, I think a lot of things can be seen from the covariance matrix. So as can be seen from these two propositions there. Okay, so if the covariance matrix is a diagonal matrix, then this joint normal random variables are independent random variables. Okay, and if covariance matrix is block diagonal, okay, so that they can have the block in the diagonal things here, then the joint normal random variable can be divided into different collections, right? Partitioned into collections, and all these collections are independent collections of random variables. Okay, so that is pretty nice to see that. Okay, because in many practical applications that to show that two collections or three collections are independent collections of random variables, then if these random variables are joint normal, then we can see it. We can see this from their covariance matrix, as stated in proposition 7.8.e. Okay, so that is the general property we have here. Okay, so I give you the essential parts about the joint normal random variables. Okay, and I hope that these propositions will be very effective for you to facilitate the future studies in many different disciplines, because normal distribution is very important in many situations. Okay, so a solid knowledge about normal random variable will be very effective in your further study. Okay, so I stop here. Okay.